Okay, we're back. Okay, this right here is a pulse, and what it's showing is a couple characteristics. First off, we've got this area. First off, is it ideal or non-ideal? Well, it's non-ideal because it's got this smooth shape. An ideal pulse, remember, looks super sharp. It's an instantaneous transition from the low region to the high region and back down. But this is a non-ideal pulse. So let's talk about this guy in the middle right here. So it's going, this right here, this time period in between here and here. These guys. What is that? That's the pulse width. It's basically a region of time, it being right here. Let's pretend each one of these blocks is a millisecond. So 1, 2, 3, 4, 5, 6, 7, 8 milliseconds. That's our pulse width. Okay? What is this guy up here? Well, this is the rise time. The time it takes to go from 0.10 of its 10% of its amplitude up to 90% of its amplitude. That's the rise time. It looks like the rise time takes 1 millisecond. Okay? So, while we're here, let's talk about, we already talked about frequency and period. Let's talk about duty cycle. So let's say I've got this waveform here. Let's go ahead and draw that. How about that waveform? Okay. What is the duty cycle of this waveform? Okay, first off, we got to figure out the period. Start here and there. What's that time right there? So let's pretend these again are 1 millisecond. So it's 1, 2, 3, 4, 5, 6, 7, 8. 8 milliseconds. What's our pulse width? Well, this is an ideal pulse. Looks like it's 2 milliseconds. So the rest of it, again, duty cycle, how much time it's on. So it looks like it's spending 6 milliseconds off and 2 milliseconds on. But again, just use these two numbers right here. It's the ratio of those. 2 milliseconds, 8 milliseconds, times 100%. Duty cycle, 25%. Okay? Alright, let's go down to these next one here. Oh, geez, let's make some space here. There you go, how about that? Okay, so it's asking, what pin number is this? Okay, so we're looking at our device from the top, and it's got this funny little hole in it, or this little break in it, or a little notch in it, whatever it is. Well, that's pin 1, and just go counterclockwise. So 1, 2, 3, we're at pin 3. Rest one's 4, 5, 6, 7, 8. And as you've seen in lab, normally this guy here in this lower left, that's going to be your ground. This guy here in the upper right, that's going to be your V in high, the power of the chips, remember? So we were using dual line pins, the ones that we put in the protoboard there. And that's where those guys are normally located. So always remember that. Always put a ground, always put a V in. But this guy has a side profile that looks like this and a front profile that looks like this. Is that a through hole or a surface mounted device? That one or that one? So one of those 3. Okay, what's a through hole or a surface mounted? Well, look at it. It's not going to go through any holes. Put it on a printed circuit board. There's a hole right there. Right there. These guys are not going to go in there. So it looks like it is a surface mounted device. Okay? Okay, let me draw some basic gates and fill in the truth table. Okay, there you go. So identify the basic gates and fill in the truth table. Go ahead and pause and give it a try. Okay, we're back. Okay, what's this guy right here? That is a NOT gate. Warning. All it does is basically it takes the input, swaps it, and gives you the opposite output. So it inverts it. So A comes in a 0, comes out high, 1. A comes in a high, X comes out 11. Okay, what's this guy over here? This guy is an AND gate. And an AND gate produces a high output only when both inputs are high. So go right to the end. So let's fill out the rest. All possible combinations are 0, 0, 0, 1, 1, 0. So again, it's only high when both are high, so that's a 0, that's a 0, that's a 0. What's this guy over here? The only other one that we got out there, the 3 basic gates, that's the OR gate. So that is high when any input's high. So we'll call it possible combinations. So anytime there's any inputs high, is this block right here. 1, 1, 1, 0. Okay? So let's go down to some basic logic functions. Okay, so there's 2 simple basic logic functions. What do you think they are? What do you think this guy is over here on the left? Well, it looks like there's 3 systems, 1, 2, 3, talking to 3 other systems on this side. There's like a single line in between right here. So what that is a multiplexer. Basically, it's taking, just think about this. Okay, A to D, and then the time switches, and then B and E talk over the same line. Okay, so that's a multiplexer. Well, this is a multiplexer. What is this here? That is a demultiplexer. It's taking the serial data and spreading it out to other ones. Basically, you gotta have one mixed together. Okay? What's this guy on the right here? So it looks like you got 2 numbers coming in. Up here. You got a carry in coming in. You got 2 things coming out. A sum and a carry out. Oh, that's an adder. Okay? So it's just taking our 2 numbers, adding them together, and if there's a carry in with it, it's going to put them together. It's going to come up with a sum. It's a carry out. It's something that's over the sum. Okay? We'll get into those a little bit more. Okay. Last questions here. We're almost there. Okay, what is the advantage of using PLD versus fixed function logic? So let's go ahead and pause. Okay, so what do you think of that? All right. PLDs. First off, you got to know what PLD is. It would be hard to answer this question not knowing what it is. PLD is a programmable logic device. What's fixed function logic? It's using these basic things right here. So this guy: multiplexers, demultiplexers, code converters, decoders, encoders, counters, registers, comparators, everything. Again, what's the advantage? PLDs are a single device. So it's one device versus a fixed function logic, which is a multiple number of devices. But the advantage lies in the fact that it can be easily changed. Okay? Once you know the programming language. Fixed function logic, it's one of those things, once you've got it, you've built the circuit, printed the circuit board, it cannot be easily changed. Okay, so once you know programming language for PLDs, it's easy to go ahead and change it, okay, without doing a lot of hardware. All right, while we're on it, topic, what is VHDL? Pause and think about it and come up with your answer now. Okay, we're back. Okay, what is VHDL? Well, first up, it stands for VHDL. So, hardware definition language. That's the HDL. Hardware language. What's this stand for? That stands for VHSIC. Very high speed integrated circuit hardware definition language. But what is it? Well, it's a language used to program logic devices. Okay, there's a bunch of different languages out there. This is the most common. Alright, so hopefully this is a good review of Chapter 1 and walk through this, and there's a couple example problems in the book there too. It has some answers in it. If you got any questions, send me an email and we will move on to Chapter 2.